I have been preparing this talk with an intention that I can give some views of physics of radiation oncology. It is the audacity of the principal of Government Degree College, Sumbal, Professor Dr. Shabina Iqbal Shawl, who is very enthusiastically supporting all faculty members to have interaction between them, to have exchange of ideas between different faculties of the college, and have some interactions with the students where students uh, can have some eye on what's going on around the globe, other than that of the academic subjects that they have been studying in the college. So in this video, the idea is that I will give a brief introduction of physics of radiation oncology, and this is an open field for especially for medical and non-medical students who can make a bright career in this field. So the intuition of giving this presentation is only scientific in nature. I mean, uh, the only thing that I want to convey here is the subject itself. So you can see the title of my talk is Physics of Radiation Oncology. The contents of my presentations will be radioactive materials, ionizing radiations, non-ionizing radiations. Then I'll be talking about different kinds of radiations that we make use for the treatment of cancer. As everybody knows, what cancer is actually, it's the growth of the unwanted cells, the cells that does not support the life. So the point of contention here is that what could be the various methods that can be used to kill the cancerous cells without killing the good cells which are supportive of life. Then I'll be giving a brief idea about the dosage for the treatment. Uh, then finally, I'll be talking about the most advanced technique that's used in the modern world, where doctors are using special technology in consultation with medical physicists. That's image guided radiation dose. So this is a very latest technology that's being used by the doctors for the treatment of cancer. So to start with, you can see on board there's a table kind of thing. We call them Maxwell's equations, and you have Maxwell's equations in differential form and in integral form. Believe me, all the technology that we have all around us, these set of four equations are the basis of all that technology. At least in the domain of communication and transmission of energy from one point to another point. If I have to speak within the context of the subject, then I'll certainly make these equations equivalent to the revelations. I mean, they are like revelations from God that can be translated into all format of the technology that we have around us, from mobile phones to transformers to televisions. Uh, the core of all these technological developments in the modern world is based on the set of these four equations. We call them Maxwell's equations, and you can see there's Gauss's law, there's Faraday's law, then there's Gauss's law of magnetostatics and Ampere's law. So these are the very beautiful equations that really have the role in modern aspect of technology. Now, if we look at the electromagnetic spectrum, so what is electromagnetic spectrum is the overall radiation that's being emitted by say sun. So it has a range of frequencies coming out of it, and only a portion of radiation reaches to us because of the atmosphere and the magnetic field uh, that's there shielding Earth because of the spin motion of Earth. Now, this diagram is very clear here that you can see that there is visible spectrum, and with respect to me, if I go to the left to the visible spectrum, then the wavelength of the radiation is very large. If the wavelength is very large, that means the energy associated with the radiations that come out of these devices, their energies are very limited. So if I make a comparison between a person who is sitting in a farm field in an open sun, he will receive many fold radiations in comparison to a person who is inside a room watching television, or having a mobile phone, talking on mobile phone, listening radio. The amount of radiations that will interact with this man inside the room, the quantity of that radiation and the energy of that radiation is very small in comparison to a man who is working in a field outside in a farm, because he's suddenly receiving the visible radiation from the sun. And we can see that the energy of the visible radiation comparably is more than that of the radiations that are being emitted by the towers, that are emitted by the satellites. So the point of getting some kind of effect from the radiations that are emitted by these electronic devices, that question is out of mark. But still, the research is going in this field, and there are reports where people claim that there can be the side effects of the radiations that are received from these devices. But to us, if we see if we see the middle of this electromagnetic spectrum is the visible light, so all the time we are receiving this visible light, and certainly the quantum of this the radiation, the quantum of energy of this radiation is more in comparison to the radiations that are coming from the towers. Now, if we go right to that with respect to me, the wavelength is getting very small, and the energy associated with these radiations is very large. Now, these radiations certainly can have implications. They can have good. They can be used. They can be generated, and in that point of view, they can have very good implications. And in some other cases, it can have very bad consequences. When it comes to cancer, we can use the same radiation to kill the cells, but the same radiation can be the original star to create tumors and cancers in the human body. So the role is dual here. It's not like the radiation is the only solution for causing cancer. But radiation can be used as a means to kill the cancerous cells. So it has a dual role. It has a dual role as long as the biological life is concerned. So you can see from this photograph all kind of technologies that are used here, from towers to televisions to DHT to bulbs. These radiations are non-ionizing radiations. They cannot cause any grave kind of problem in the human beings, because non-ionizing radiations mean that they cannot break the atoms, if you cannot eject the electrons from the atoms, then this kind of radiation is safe. At times, if I think about 2,000 watt room heaters, so they are emitting a lot of thermal radiations. We are receiving them, and we take that radiation in order to heat our bodies. So these radiations, as long as the range of their wavelength is concerned, they don't seem to be have very grave implications. But if we go into the domain of gamma rays, X rays, then certainly in that case, the outcome of the radiation can be something grievous. Now, the very fundamental question is that what is radioactivity? So, all of we know that we have a set of series of atoms in periodic table, and every atom has a nucleus, and some nucleuses are unstable, and most of the nucleuses are stable. So, the stability and instability. So, if I have to tell you. Unstable nucleuses, these are the nucleuses which are radioactive in nature. Unstable means that there happens something to these nucleuses spontaneously. They lose their original structure, they give birth to the daughter nucleuses, and in addition to giving birth to the daughter nucleuses, there is emission of radiations. Alpha, beta, and gamma radiations come out of these nucleuses, and we call such nucleuses as radioactive nucleuses. And the materials which are made of these radioactive nucleuses are called radioactive materials. Now, fundamentally, there could have been many reasons for these nucleuses to be unstable. In fact, it's not fully clear that why some of the nucleuses are unstable. We don't have a complete theory for them, but there are some acceptable theories which can explain that why certain nucleuses are unstable and some other nucleuses are stable. So, in case of instability, we have if we go through the binding energy curve of nucleuses, we find that the binding energy per nucleon of some of the nucleuses is very large, and some other nucleuses the binding energy is very small. So those nucleuses whose binding energy per nucleon is very small, these nucleuses are unstable nucleuses. They break down into their daughter nuclei, and while breaking down to the daughter nuclei, they emit radiations. So we call such nucleuses which are unstable, owing less binding energy per nucleon. We call such materials as radioactive materials, and this phenomenon of breaking down of nucleuses spontaneously, naturally, we call it radioactivity. There is another way of understanding that why these nucleuses are unstable. That is, since nucleus has nucleons in it, and the nucleons of the nucleus are neutrons and protons. Now, in these nucleuses, which are unstable, the number of protons is large, and in comparison to the number of neutrons. So this can be another attribution to the instability of the nucleus. Even though there is nuclear force involved in these nucleuses, which binds all of these nucleons together, but the electrostatic repulsion increases if the mass number of these nucleuses is large and the number of protons exceed the number of neutrons. The electrostatic repulsion between the protons can unstabilize the nucleus, and they become they behave like radioactive radioactive atoms, radioactive nucleuses, radioactive materials. On the other hand, unstable or unstable, stable or stable, they don't break down into their daughter nuclei spontaneously. They are stable. Now, to move on, so you can see that when this nucleus breaks down, while breaking down, it can emit radiations, it can emit energy, it can emit particles. Now, see, here's a very simple photograph of penetration power of different types of radiations. So, all the radiations do not have the same kind of characteristic. They do not have same powers. They do not have same energies. If we see here alpha particle cannot even penetrate a thin piece of paper. And then if you see beta particles, which are electrons, which are electron like particles coming out of nucleus, they can penetrate the piece of paper, but they cannot penetrate aluminum foils. Then X-rays, highly energetic particles, and these photons, X-ray photons, they can penetrate a paper, they can penetrate aluminum foil, but they are blocked by the lead. Then you can see gamma rays. They are highly energetic rays. They can pass through the paper, they can pass through the aluminum, and they are again blocked by the lead. And finally, if you see neutrons do not have any charge. But if we have fast moving neutrons, they can pass through the paper, aluminum foils, lead foils. Then for them, in order to stop them spreading around, you have to build concrete structures so that they cannot pass those structures. Now, this is the point that's very important. What is an ionizing radiation? You have an atom, it has a nucleus, and electrons are if I say classically, electrons are revolving around this nucleus. And, and when you have sufficient energy, so that the outer electron of this atom is ejected from the atom, we have an ion, a positively charged ion. So the energy that has been utilized, this energy is having such a power that it can certainly get an electron out of this atom. This kind of energy is called ionizing energy. So ionizing energy certainly makes a role. It makes a role to destabilize a situation. To destabilize a situation where we are dealing with the biological cells. And if I think in terms of a biological cell, a cell can be thought as an individual having nucleus, and this nucleus has chromosomes. These chromosomes are made of DNA, and finally the DNA is made of different kinds of atoms having some specific positions in the DNA molecule. Think if we are able to ionize the atom of this DNA. If we ionize the atom of the DNA, the atom will be unstable. Okay, the DNA has the capability. In certain cases, it can replicate itself again, and can mutate in such a way that you will have the same kind of DNA back in action. But here seems to be a point that this seems to be a point where we can certainly make the change. If we ionize the atoms of the DNA, certainly a very strong state of disturbance will occur in the DNA molecule, and the DNA molecule can undergo different states. So here the point of contention comes in action, that what should be the energy, what should be the dose, and what should be the circumstances that can be used in order to kill the cells that are not favorable for the life in the human beings, whom we call cancerous cells. So you can see this. This is ionizing radiation. So ionizing radiation is capable of creating disturbance to the atoms. When atoms are disturbed, the DNA molecule is disturbed. When the DNA molecule is disturbed, the chromosomes are disturbed, and finally the cell is disturbed. So if if the situation is dealt in such a way that everything goes off, so the cell will have to go, the cell will have to die if there is no reconstruction happening in such a way that a cell can come back to the life, a cell can self-replicate itself to its original form. But in certain cases it can, and in certain cases it cannot. Now, the dose that I was talking about. So there is a need of calculation that suppose a person is having some kind of cancer. Now this cancer can be localized cancer or in the form of a tumor. Even this tumor can have a mobility. It can move from one position to another position. So there are many parameters that the doctor has to think, and for that he has to make certain calculations, and these calculations are purely mathematical in nature, and the accuracy of these calculations is great, is very good, as long as the application of radiation is concerned. Now, I want to put your notes here on this slide. There is a quantity called as Rankine equivalent man. Now, this Rankine equivalent man gives us the measure of dose that's absorbed by a person per year. Now, this Rankine equivalent man for 1 year is 5 rem. It's a safe amount of radiation a person can receive in 1 year. So if a person receives Rankine equivalent man greater than that of 5 rems, then it's not considered to be the safe zone. But if a person receives the radiations less than that of 5 Rankine equivalent man, then there is no danger of getting some kind of cancer or some kind of disease from the radiations. So you can see here the average external radiations received per year. I mean, a person going into the field, sowing seeds, doing a lot of farming, selling things on road, walking on road, doing some exercises in the road. Certainly, he or she is receiving radiations from sun. Okay, so the average amount of radiations a person receives per year is 100. It's 100 millirem. It's not rem. There is some mistake in it. Okay, it has to be 100 millirem. And then, in addition to this, if a person undergoes through artificial radiations, like one has to go for X-ray, one has to go for MRI, one has to go for CT scan. So if a person goes through all these radiations for 1 year, the overall calculation of the dose, the Rankine equivalent man for him is nearly 100 millirem. So the total radiation a person on an average receives from natural resources. Now, natural doesn't mean only sun. I'm sitting in this room, the walls are there, they're concrete walls, there is cement in them, and certainly there are radioactive atoms and elements in them. They are emitting radiations, and I'm exposed to those radiations as well. So there are radiations that are coming from the soil. Okay, there can be a zone where the radiations coming is very large, and there can be some another zone where the radiation coming is very less. But we are receiving these radiation, and these are ionizing radiations. And you can see that if you sum up all the radiations, natural as well as artificial radiations, per year, it comes out to be 200 millirem, Rankine equivalent men. And if I have to put it in terms of rems, it is 0.2 rem. Now 0.2 rem is very, very less than that of 5 rem. It's nearly 1% of 5 rem. So it means the radiations that we are receiving from natural resources and from artificial resources does not exceed zero point 0.2 Rankine equivalent man. So if we see from the book is saying us that you are safe. You are safe even if you are subjected to some kind of artificial radiations, right? So from this point of view, it becomes clear that this is an ionizing kind of radiation, and this radiation that we receive is very less when it will cause some kind of damage to the man. So the radiation that are coming out of our mobile phones and that are coming out of the towers, I don't find that what will be the state uh, of severity that they might be causing to us. They might be a source of some psychological disorders that can develop when a person is watching a lot of mobile phone, it's heating up and all that. But I don't think the heat generated by the mobile phone can have such adverse effects. Other effects are certainly infinite. A mobile phone can have a lot of things that you can watch on it. You will lose all your social charisma, social character, your family, and all that. But the radiation, as long as the radiation is concerned, that radiation does not seem to have any kind of wrong implications on the biological sides. So now, suppose a person is suffering from cancer, and there is some development of cancerous cells, the cells that do not suppose that do not support the life the man or a woman is living. So in that case, a medical doctor has to decide all the clinical implications of that. But from physics point of view, the role is only of the particle accelerator. So what is a particle accelerator? So you need a highly energetic radiation. When this highly energetic radiation will hit the atom will be ionized, and now this ionization will decide that what will be the outcome of that ionization, right? Whether the cell will die in some span of time, the DNA molecule will not be in a position to replicate itself, or the DNA molecule will be in a position to repair itself, but it will repair itself in a very wrong way, or the cell will completely die. Now the point is that what is a particle accelerator? A particle accelerator is an accelerator where you generate the highly energetic radiations, highly energetic X-rays, photons, material particles like electrons and protons. And we have nearly 300, no, I think 3,000, 3,000 particle accelerators around the globe. And there are places around the globe where we have particle accelerators under the roads. And these particle accelerators are very huge. And these particle accelerators can be used for research, and at the same time, they can be used for the treatment of cancer, and they can be used to cause the wrongdoing bacteria to die, and it has many implications that it can be used of. So here I would like to show you a general movie on particle accelerator, and I would love to see watching it, and you should also watch it if it runs. So it's running. You can see it's a machine, it's a particle accelerator. Okay, the particles are accelerated to the speed of light, and you are giving a strong magnetic field. You are collimating the beam of highly energetic particles, and they can be used in medicine, they can be used in industry, and there are many types of accelerators, right? Cyclotron is there, synchrotron is there, linear accelerator is there. Yes, nearly 30,000 accelerators in action. So this video is from IAEA, International Agency Atomic Energy. So let's proceed. Oh, it's coming back. I want the next one. Okay, now see, we understand now that when we have radioactive particles, radioactive nucleuses, they break down into the daughter nucleuses. They emit radiations in terms of alpha particle and beta particle, gamma rays or X rays, and you can see the penetration power of these particles again. But at the same time, if you see the penetration of these radiations in terms of a human being, so you can see alpha particles. I mean. Upon collision, several terms of micrometer. So the penetration of alpha particle is very, very minute. You can see here, and beta particles can go some millimeters inside, and gamma rays and X rays, they have a very, very strong penetration power. They can pass through our bodies. Now, now coming to the photon interaction with the tissues, I mean, certainly the radiation that's out there, it's interacting with our cells, with our bodies, and what can be the various radiations, and what could be the outcome of these radiations. So the photons, they can indirectly cause ionization in a medium, and that can be the reasons for to damage the DNA molecule, and the photon can create some kind of a free radical, because these cells are mobile within some fluids, and if a photon is energetic enough, it can cause indirect ionization, and that indirect ionization can lead to damage the DNA of the DNA molecule. So the other scatterings, like coherent scattering is there, photoelectric effect is there, Compton interaction is there, pair production is there. So these are different kinds of interactions, and each interaction has its own consequences. Say, for example, if I talk about photoelectric effect, so it can have highly energetic photons, and it may eject the electrons from the inner orbits of an atom, and when an inner electron is out, it will cause disturbance within the atom, and there will be emission of some radiations due to that atom. Similarly, you can this Compton interaction is it knocks out the electrons, and creating the free radicals, and then causing damage to DNA molecules. So photoelectric effects have main implications in diagnostic imaging, where we are more interestingly looking for the images of the things that are going on. And the Compton kind of interactions are useful in damaging the DNA of the cells, which are multiplying, but they are not supportive of life. They are basically something that opposes the life to exist in its original form. And then there is pair production, in which you can have a photon, and this photon under certain circumstances can break down into two particles, like electron and positron, and these electrons and positrons can further create some kind of reactions within the system. So this is a pictorial way of seeing these kind of interactions that can take place, and depending on the energy of the photon, we will have that state of interaction with the atoms and the electrons that are revolving around these nucleuses. In certain cases, the inner electrons will come out and will give birth to X-rays. In certain cases, the outer electron will be ejected, and there will be a direct formation of an ion. There can be some other kind of interactions that take place. Now, talking about the clinical application of radiation therapy. See, radiation therapy is it's a tool used by doctors, the medical doctors, and they consult medical physicists in calculating the dosage for particular patients to destroy the cancerous cells in the human beings. So, so this kind of it has the clinical applications, but it involves some rigorous mathematical calculations, and when these and the very complex thing here is that every individual is different. Every individual has different kind of system, has a different mechanism, a different state. So every time you have a patient, you need a calculation. You need a calculation of the dose that can be applied to the patients to get some optimistic results. So this is what it states: the therapeutic use of radiation is based on its biological action. So radiations are there; they are interacting with non-living matter. They're interacting with living matter. But here, what's most important is that how it interacts with the biological tissues, how it interacts with the biological cells. That's what makes it clinical. So otherwise, everything is radiation in all formats. We can see radiations are there. Even there are radiations that are developing in our bodies. We have vitamin K, and vitamin K is a radioactive element, and it can emit radiations, and two ionizing radiations. Now the radiations that we receive from these towers are mobile phones. So let's move on. So what's a dose? A dose is basically the amount of radiation that can be absorbed uh, by the atoms, that can be absorbed by the atoms or molecules, right? So this radiation dose is measured in it has a unit, we call it gray, and uh, depending on the type of stage of the cancer, as all of we know that there are stages of cancer where a stage can be initial, it can be middle stage, or it can be a saturated stage. So depending on the stage of cancer, the doctor will prescribe the treatment. The doctor will go through the clinical implications, and in consultation with the medical physicist, so they have to calculate the dose that they will give to the patient, and what will be the fractionation of that dose. So you divide that dose into many sessions, so that there is some systematic way through which the outcome of the treatment is on the positive side. So here we say that if we have a solid tumor, the dosage ranges from 60 to 80 gray. And if we have a soft tumor, now this soft it is making things very complicated, because when you have something soft, that means it has more mobility. So when you have to select the target, you will image it, and you will select. By the time you have to impose radiations on that target, there maybe the tumor is drifted a little bit from its original position. So in that case, the range of the dose is between 20 to 40 gray. And mathematically speaking, this dose is mathematically defined as a derivative of energy with respect to the mass. And this dose is, obviously it's clear that it's measured in joule per kilogram. So this joule per kilogram is 1 gray. So again, if I read these lines, the absorbed dosage of the radiation is expressed in the units of Gray. So the dosage is expected in terms of fractions, and each Gray is made up of two fractions. The dosage of fractions vary from type and the category of. These are the mathematical calculations that has to be carried out, or they have to be coded, or you have to write a program for that, so that you can put up the various parameters in calculating a particular dose for the particular patient. And this is a linear and quadratic model most probably used, and here the symbols have their own usual meanings. You can screenshot it, and this equation can be used to calculate the amount of radiations that can cause what amount of ionization, because ionization becomes the core of the whole situation. It's the ionization that can be the origin of destroying these DNA molecules, and that too in vitro and vivo. So you are making calculations in both the states. So vitro here, it means you calculate the absorption dose for non-living things, and vivo here refers to calculate the absorbed dose for the living cells. Now, see, here is a very simple picture of the double helix. It's sometimes people have different names for it, call it signature, they call it the core unit of life. And you can see here that if you use the radiation has to do the job. If it's a DNA molecule of a cancerous cell, the radiation should be able to break down it by ionizing the atoms that this DNA molecule contains. So once the DNA molecule is, once there is a disturbance, then the molecule will try to attain its original state. So all of these things will depend on the quantum of radiations that it will receive. And obviously, the results, the outcomes will not be exact, they will be probabilistic. Now you can see, so when we ionize a DNA molecule, so there are various possibilities that can outcome from this. You are ionizing the atom of a DNA molecule, and okay, nothing happens, and cell is able to, the DNA molecule is able to replicate itself and recover itself in perfectly exactly in the same way it does. It should be the case with the cells which are good, which are life supporting cells in the human beings. Where if we are imposing some radiations on some portion of the body, obviously there will be good living cells which are supportive of life. We would always love to have a kind of interaction between radiation and the DNA molecules of these cells, where these DNA molecules can repair it themselves and come back to their original states. The other one is where you can permanently damage the cell. You will ionize its surroundings, cause a formation of radicals, and destroy the cell, and the cell will no way be in a position to retain its identity. And the final one is that when there is the damage, you're causing the damage to the cell, but the cell is not in a position to replicate itself in the same state as it was. So cell is incorrectly repaired. So this incorrectness can be the result of the exposures. If a person is subjected to some kind of exposures, where the radiation is intensely falling, and it can be the cause of the cancer here in this case. So in one case, there are probabilities of repairing the cell correctly. In other cases, the cell will die permanently, which should be the case when it comes to the treatment of the cancer patients. And then comes the category where cell is incorrectly recovering itself, and this is the case that where a person can be subjected to can have a disease like cancer, or where the cells will repair, but they will repair in a bad way, giving birth to the cancerous cells. So this third category, where a cell is incorrectly repairing itself, this is called as a stochastic effect. And where we are able to kill the cell completely, this is a deterministic effect. You're completely damaging the cell from its roots. Now, firstly, they're used to have classical way of treating cancer patients, where we had to locate the cancer. We would take some photographs, we would use some X-rays or some other format of imaging radiations, and we could photograph the cancer, and then as long as the external radiation is concerned, we will fix the target, and use all the formats in the laboratory, and finally apply the dose on the design target. The problem in those classical radiation therapies was that the location could be there was one. Suppose a tumor is located at position X, and it was thought to be at position X, and you were using the radiation at the position X to kill the majority of the cancerous cells. But that's not the case, because there is some state of fluidity, there is some state of mobility involved within our bodies. A tumor can be a little bit mobile, and it can move from one, even though that movement can be very very small in dimensions, but that smallness of dimension will certainly expose good cells, a large number of good cells, where these good cells can be killed. So now we have technology is advancing in all the formats, mostly in developed countries, and also the developing countries are developing such tools by which they can, at the same time, they will image the tumor, and once it's imaged, and this image will guide the radiation to fall on the target. So the medical imaging that's used in the modern world, it really makes the treatment of cancer extremely effective, because we are strongly successful in delivering the dose to these patients at the right time, at the right position, at the right in the right quantities, and certainly the outcomes of the results of the treatments that are done all around the globe, they are improving day by day, and they are improving because of the imaging. And one of the techniques that's purely used is image guided radiation therapy. So this is the kind of thing that I was talking about, that you have an overall instrument which has both the radiation source, that from where you'll get the radiations. Now the radiations that you're using, you have different sources of radiation, and the other part is the imaging. So both the technologies are incorporated in the same apparatus, where you image the track, and you embed the radiation to the track. In this case, the probability of getting the good results is very large, is very very large. So this image guided radiation therapy is mostly used for the cancers in lungs, liver, pancreas, prostate gland, and some other formats of tumors. We can locate them, and you can execute not only radiation, you can perform some kind of surgeries at the time of imaging that organ. And this is what I was talking about. So you in image guided radiation therapy, you have an incorporated scanning system. where you have to apply the radiations to the target, but at the same time you have the technology available that can locate the presence of these unwanted cells, these cancerous cells. So the machines will be used to deliver the dose at those points, and they will be identified by, say, MRIs or PET scans or CT scans, which are actually embedded in the whole system. It's not like that you will take a photograph in one room and then you will be given treatment in another room. So it's a complete system there where all of these scientific phenomena are carried out, and the outcome of this radiation treatment for cancers comes out to be very, very good. So this is what I was talking about. These kinds of images that could be developed, and you could bombard the appointed target, and you could apply the radiation dose. So here you can see a photograph where you have two kinds of things happening at the same time. You can find some light. This light is basically an identification of the tumor, or the point of contention can be any different. It all depends on the medical doctor, what kind of treatment they are giving to the patient. But as a medical physicist, you can say here that you are carrying out these operations. You are carrying out, you are bombarding those radiations in a very, very precise way, while the probability of executing any kind of error is very, very small. You can locate an object which you want to destroy, and you can hit that with very, very good accuracy. So here you can see another image. So the patient has to stay at one in one state, and the machine is going to do the rest of the job. The machine is going to move in all the angles to expose the tumor, and irradiate that tumor with the effective radiation, to photograph it at the same time and execute the radiations on the tumor at the same time. So the same thing. Here I should tell you goodbye, and I have just tried to give you a brief introduction of physics that's involved in radiation therapy. Okay, thank you.